two of our HBase colleagues from XiaoMi in China. They couldn't be with us today due to visa issues. They couldn't get their visas approved to come and be with us in person today. So what we actually have is they took the time to prepare a pre-recorded video for us. So we're gonna play that for you guys now. And then afterwards, they're actually on a web call with us. So we're gonna open up for Q&A. You guys can ask me the questions. I will type the questions to them. And hopefully, if all goes to plan, you'll actually be able to hear their responses back.
Everyone, we're sorry that we can't attend this meeting, but thanks committee to offer us this chance to give the talk like this way. There are two parts of our talk. First one, I will talk about several problems we met and how we solve them. The second part, my colleague Zheng will introduce how we improve replication. Okay, let's start our first part. First part, I will show you some problems we met in practice and how we solve them. Our first problem is how to satisfy the regular demand of scanning table without affecting other requests. As we know, scanning HBase is very expensive, especially when there are multiple scans that may block other requests. But many data analyses are based on scanning data by MapReduce or Spark. We need to find a way to satisfy both data analysis demands and general requests. It's wonderful that HBase already provides this feature, Table Snapshot Input Format. It uses client-side region scanner to scan snapshot directly. It means you can build region and region side and client side by snapshot files, and the client could read file directly from HDFS without sending RPC requests to HBase cluster. When it comes to practice, there is a problem that users don't have permission to these files, neither the reference files nor the H files. Fortunately, we found HDFS ACL can help us solve the problem. As we know, HDFS ACL can grant different accesses to a couple of users besides owner and group. It can support up to 16 users because there are 32 ACLs in total, and for each user, it has a user ACL and a default user ACL, as the figure shows. Thus, we implemented a HBase ACL manager that can help grant read access to users. When we grant a permission of namespace or table to user, HBase ACL manager will check if the permission contains read access. If so, it will traverse all files and directories under the table or namespace and grant ACL to the user. Then, when user creates a snapshot of this table, HBase ACL manager will help grant access to the snapshot manifest. By this way, users can scan table snapshot directly. The second problem is how we prevent data from lost or being contaminated when users operate incorrect. Our users are not HBase experts. They may make mistakes sometimes. There are two common problems we want to solve. One is user regret dropping table, and the other one is user delete data by mistake or write in wrong data. To prevent the problem happen, one thing we did is soft deletion. It will take a snapshot of the table before we drop it. Then, when user regret dropping this table, we can restore the snapshot. And there is a cleaner thread which will help delete these snapshots after a certain period, for example 1 week. So user can have 1 week to decide if they really want to drop this table. The other thing we did is backup snapshot to heterogeneous file system. Since the backup is the last choice when we need to recover data, we must make sure it's 100% work. Thus, we choose a simple design of backup logic. We construct a HBase backup manager to export a snapshot of important tables to another file system every week, and use meta files and data files to help deduplicate. Like the figure shows, there are multiple backups of reference files and a simple pool of data files. Then, if user delete data by mistake or writing wrong data, we have backups to help recover correct data. Besides, HBase Backup Manager will help manage these backups, delete a snapshot directly, and verify these backups by scan snapshot, like we mentioned before. Okay, here comes the last problem. We found the restart of a small cluster is often stuck at log splitting. After we dig into logs and code, we found the cause. Log splitting has a bad performance or even not working when the number of regions is very large. Let's look at the process of log splitting and explain why this problem happened. All design of log splitting is reading entries into a map whose key is region name. Then get the biggest chunk to write every 500 milliseconds. For each region, it will create a log writer to help append entries into recovered file. These log writers will only close until log reaches to the end. Apparently, there are too many log writers opening at the same time. Since each region has a log writer and each log writer has a HBase client, too many log writers can lead to two problems. One problem is too much space needs to be reserved at the same time. As we know, name node need to reserve some space for a new block. This is the equation of reserved space when we do log splitting. When number of regions is big, name node may fail to assign enough space for a new block, especially for small cluster whose remaining space is small. The other problem is too many HBase streams created at the same time. Since each HBase client will create a stream to data node, this is the number of streams will be created. When number of regions is big, streams need to be handled for each data node, maybe more than 4,000. That will make log splitting fail. Clusters all facing this problem, no matter they are large or small. According to this, we know the key point is to limit the number of opening log writers. Here is our new design. What we call get chunk to write. We only return the chunk whose size exceeds max heap usage. Once we get the chunk, we write it into recovered file, then close it immediately. After reading all entries into memory, we start a thread pool to write the entries into files and then close them. Thus, the number of log writers will be no more than the limit of the thread pool. It can solve the two problems we mentioned before. Also, we tested the performance. When speed 1 log, we can see in most situations, the new design has a better performance than the old one, and the 32 seems to be the best choice. We also test the performance of restart of a cluster which has different number of regions. Let's look at the table. We record the total hlog size and the time cost to speed log, and get throughput by using size of hlog divides cost time. The result is as the figure shows. For one certain series, it almost has no change as the thread count increases, but more regions result in less throughput. Since more regions means more recovered log files will be generated, we can get the conclusion that the time of log splitting depends mainly on number of generated recovered log files. Here is how to enable this feature and some advices on the configurations. That's all for my section. Thanks. Please welcome Zheng to introduce the second part.
Hi everyone, I'm Zheng and I come from Xiaomi too. I will introduce some important improvements contributed by Xiaomi to HBase replication since last HBaseCon 2017. In the past days, we encountered many problems when using replication and developing some advanced replication features such as serial replication and synchronous replication. We found that the previous replication framework is not very reasonable, so we did some work to redesign the replication framework. The first section, we introduced the new replication storage layer to store the replication matter, such as replication peers and replication queens. Also, we refactored the replication task flow, and this is section 2. Finally, I will introduce problems we found in the first version, serial replication, and how did we fix those problems. The first section, new replication storage layer. The original replication storage has those problems. The interface definition is not very clear and fuzzy. And some interface classes are used for client, but others for region server. In fact, we can integrate those together. Another important problem is that the original storage layer has no consideration for the abstraction for table-based replication storage. So we did some refact. Here is our implementation. We have very clearly defined two interface classes, replication peer storage and replication queen storage. The first store replication peer matter and the second store replication queen matter. After that, we re-implement the zookeeper storage, and the table-based replication storage is still under development. In the upper layer, the HMaster and the region server and the replication tools all share the two storage interface classes. Section 2, replication task flow. The original replication task flow is straightforward and crude. The client request to replication admin, and the replication admin writes some data to zookeeper and then just return to client. At some point in time, the region server receives the watch event and finish to add a new replication source asynchronously. But there are some problems. Firstly, we expose the replication implementation to HBase client, so the client must be allowed to read and write the replication zip node. Some user may mess up the zip node, and the request will not be routed to HBase master or region server, so hard to authenticate the request, and no code processors for the interfaces. On the other hand, region server handles the task asynchronously, so client want to know whether the task is success or not. The notification may last too, then region server is not alive. What's more, it's hard to implement the more complex task flow for serial replication and synchronous replication features. After HBase 11392, we implement the replication task flow as this. The client sends a request to HMaster, and HMaster writes some data to zookeeper, and then just return to client. But the region server still handles the task asynchronously. We fixed the first problem by delegating HMaster to handle the request, but the second problem still exists. After HBase 19397, we refactored the task flow by using HBase procedure framework. So the RS handle all the subtasks synchronously, and we can implement more complex task flow by using procedure framework. So the second problem has been fixed too. The new replication storage layer and the replication procedure have been included in HBase release 2.0.0. Section 3. Revisit serial replication. First of all, let's see why we need serial replication. We have a source HBase cluster, and the region A is located in region server 0. So for region A, only region server 0's hlog will be replicated to PR cluster. But once region A moved from region server 0 to region server 1, both hlog 0 and hlog 1 will have mutations from region A. So for region A, both hlog 0 and hlog 1 will be replicated to PR cluster in parallel. The first problem is mutations are out of order in PR cluster. We can see that in the presentation. Obviously, the put with timestamp 5 is ahead of put with timestamp 2 at the PR side. Actually, it's a disaster for POP and subsystem or message system. Another problem is data inconsistency. Because of the disordered mutations in PR cluster, so it's possible that the delete with timestamp 4 came first in PR cluster, and then we have a major compaction. After that, the put with timestamp 2 come in. Finally, the source cluster has no data, but the PR cluster has a redundant cell, which is put with timestamp 2. Data inconsistency happen between source cluster and PR cluster. Let me explain the core idea of serial replication. For each region, the region server will store region's open sinks number as its berry. So if opening a region 4 times, we will save 4 berries. The green one represents the berry in timeline for a region. Here the 4 berries divide the timeline into 5 intervals. Obviously, for a given interval, only one region server will take charge of its entries and replicate them to the PR cluster. The serial replication ensures that only when all entries in the previous interval has been fully replicated to PR cluster, the region server will start to replicate entries from the next interval. To know which sinks ID of the given region we have replicated to PR cluster, we store the last pushed sinks ID for each region. In this picture, the yellow one is the last push sinks ID. The light one is the pending sinks ID to check whether we can replicate now. If not, the replication source will sleep some time until the check passes. Okay, those are the definitions of last push sinks ID and berry. Notice that the last push sinks ID and the WAL position are two completely different concepts. The last push sinks ID is sinks ID. It's a concept in region level, but the WAL position is the latest replicated offset. for the current WAL file. So why we need to re-implement the serial replication? In the initial version, WAL entry only has an encoded region name, so we use the encoded region name as row key in meta table. But the normal row key is a full region name, so the encoded region name messed up the HBase meta table. On the other hand, we store the last pushed sequence ID in HBase meta table, but the WAL position is stored in Zookeeper. So after replicate a WAL entry, we need to update both ZK and meta table. It's hard to make them to be an atomic operation. And after HBase 19397, we introduced a new replication storage layer. Need to integrate the serial replication with it. After replicate a WAL entry, we need to update both WAL position and the last push sequence ID. To make updating them in atomic operation, we move the last push sequence ID from HBase meta table to Zookeeper and access the last push sequence ID by replication storage layer. But we still store berry in HBase meta table with its row key to be full region name. So the row key mess problem has been fixed, but the inconsistency between Zookeeper and meta table still exists. So I need to update WAL position and the last pushed sequence ID in an atomic operation. There is a case. Notice that for those intervals before the initial last push sequence ID, it's possible that two region servers are replicating two different intervals in parallel. So the latest last push sequence ID written by one region server may be overwritten by another region server. The serial replication will get stuck if the last pushed sequence ID for one region is not strictly increasing. The solution is here. Firstly, we read the current Z-node version and the last pushed sequence ID for the given region. If the new last pushed sequence ID is less than or equal to the current last pushed sequence ID, then just ignore the new last pushed sequence ID. Else, we can persist the new last pushed sequence ID by set data with the current Z-node version. And if no version conflict, then the CNS is success. Otherwise, just retry the step 1 again. So the inconsistency problem had been fixed too. Another important problem why we re-implement the serial replication is no consideration for the initialization for last push sequence ID, which may block the serial replication. By the way, we moved the serial attribution from table to peer. The difference between adding a serial peer and adding a normal peer is that we need to initialize the last push sequence ID for the new serial peer. See the corresponding step in red text. We reopen all regions in peer to save their latest berry. If no opening, the RIT region or region without any put will hide the out-of-date last push sequence ID. Then the last push sequence ID will be incorrect. In step 5, we store the latest berry as the initial last push 6 ID. After the serial PR is created, all newly written entries will be replicated to PR cluster serially. Next, I will explain how do we decide whether the region server can replicate an entry or not. After successfully adding a PR, the initial last push 6 ID will divide the timeline into 2 intervals. We want to guarantee the serialization, where first 6 ID is less than the initial last push 6 ID. No depending 6 ID is less than the last push 6 ID, so just replicate the current WAL entry. A special case is depending 6 ID is in the first range of berries. It's possible that the region is a split or merge result of other regions, so let's wait until its parents to be fully replicated to PR cluster if parent exists. Otherwise, just replicate the entry to PR cluster. Another common case, depending 6 ID is in the range of berries, but the last push 6 ID haven't reached null. So let's wait until the last push 6 ID is greater than or equal to berry 2 minus 1. Another corner case, depending 6 ID to check is located in the last interval of the berries, and the region is marked as opening. In this case, we need to wait until the region marked as open, because if the region server 1 is replicate the open region marker to the PR cluster, then it will broken the serial replication. Thank you.
All right, at this point, we're going to try now to get these guys on the phone to answer any questions you guys might have in the audience. And I'm told if you get up and use that microphone in the middle of the room, they should actually be able to hear you as well. So who is the first question?
Okay.
Hello. When will the new version of serial replication be available in HBase?
Yes, but not very clear.
Yeah. Okay. Door is responsible for the release, and we expect it will be HBase 2.1.0.
Thanks.
Okay. If that's it, thank you guys on the phone. I know you guys went through some heroics, so thank you and enjoy the rest of your day. I know it's early in the morning for you guys.
Thank you all too.